Welcome to a critical Code Ninja's security advisory. Look, right now, we're facing what I can only describe as a catastrophic breakdown in kernel privilege boundaries. We are talking about an actively exploited zero-day in the Linux kernel, tracked as CVE 2026-31431, but you're probably hearing it called copy-fail. So let's jump straight into this explainer, because this intelligence is dropping right now to give you the immediate mitigations you need to protect your perimeter. If you run a shared kernel environment or a multi-tenant host, you need to listen up because you are under imminent threat. An unprivileged local user, yeah, they can leverage this flaw to get full root access in literal seconds. We're operating in a full disclosure reality today, and my goal here is to arm you with the exact mechanics to neutralize this threat completely.
So how exactly did we get here? It's kind of wild. The groundwork for copy-fail was actually laid way back in July 2017. It was just a simple, in-place performance optimization merged into Linux 4.14. Fast forward almost a decade to March 23, 2026. That's when Coordinated Vulnerability Disclosure, or CVD, kicked off after researchers quietly reported the flaw. But that window of safety completely shattered on April 29th. Full disclosure happened, and fully working zero-day proofs of concept just dropped online. It spread like wildfire. Within days, by May 3rd, CISA slapped this right onto their known exploited vulnerabilities catalog. The threat actor weaponization is real, and guys, it's happening as we speak.
And this next point absolutely highlights the blast radius we're dealing with. The Microsoft Defender security research team went on the record stating they're already seeing, quote, preliminary testing activity that might result most likely in increased threat actor exploitation over the next few days. Basically, the storm is brewing. Why is this so urgent? Because incredibly efficient 732-byte exploits written in Python, Go, and Rust are already sitting in public open-source repos. And since these proofs of concept rely on totally legitimate system calls, they are highly portable. We're talking Ubuntu, RHEL, Amazon Linux, SUSE, you name it. If your perimeter isn't patched right now, it's in the crosshairs of even the lowest privileged account on your system.
Okay, let's just pause for a quick comms check. I need a status update from the operators watching this advisory. Drop a comment down below for me right now. Are you patched or are you vulnerable? Honestly, we practice coordinated vulnerability disclosure to force these fixes and protect the community, but we really need to gauge the actual blast radius out in the field, so let us know your current system status. It helps everyone understand the true exposure of this threat across different environments.
Now, to maintain your operational security going forward, I need you to execute 3 quick steps. First, subscribe to the @CyberTech79 channel. Second, turn on those notifications. I'm framing this as a strict security necessity, okay? You do not want to miss our real-time intelligence drops as this whole situation develops. And third, hit the like button on this advisory. Treat that like as a formal ACK, an acknowledgement of receipt for this intel. Your engagement is absolutely crucial because it forces the algorithms to push this critical data out to other defenders who desperately need to lock down their networks.
All right, let's dive into the technical protocol and see how this exploit actually ticks. Copy-fail comes with a CVSS score of 7.8, and it's a local privilege escalation, or LPE flaw. Here's the kicker. It lets an unprivileged user grab root without needing any of those complex techniques like race conditions or memory guessing. How? Simply by corrupting the kernel's in-memory page cache of literally any readable file. And because this corruption happens entirely in RAM, the actual on-disk inode is completely untouched. Think about what that means. Your traditional file integrity monitors like 8A or Tripwire, which only scan the physical disk, they're not going to see a single forensic footprint of the breach. 0. So here's the exact hyper-efficient exploit protocol. Step 1. The attacker opens an AF_ALG socket. That's essentially the user space interface into the Linux kernel's crypto API. Step 2. Thanks to that 2017 optimization bug in the LGIF AAD module we talked about, the kernel actually performs an in-place decrypt before it finishes its authentication tag check. When that check inevitably fails, it kicks an error back to user space. But, and here's the fatal flaw, a 4-byte scratch write has already fired inside the kernel. Step 3. The attacker uses the splice command to funnel that 4-byte overwrite directly into the page cache. This corrupts the in-memory version of a setuid binary, like /usr/bin/su, or maybe alters a UID right inside /etc password. Finally, they execute that corrupted binary, and bam, instant root privileges. Now, this completely shatters a major assumption we all make about container security. We naturally assume containerized environments give us strict isolation boundaries, right? Well, copy-fail exploits the shared kernel reality, because environments like Docker, LXC, and Kubernetes actually grant processes inside a container access to the AF_ALG subsystem, assuming the module is loaded on the host.
the page cache is shared too, meaning if an attacker breaches just one low-privilege container, they can leverage this flaw to corrupt the page cache and take over the entire physical machine. A vulnerable host literally turns every single container sitting on it into a glass house. So, how exactly do we lock this down? Let's walk through the actionable mitigation protocol. Rung 1 is obviously the ultimate defense, a full kernel patch. You need to update to versions 7.0, 6.19.12, or 6.1822. But remember, and I can't stress this enough, a patch without a reboot just leaves your system running vulnerable code in memory. If you can't reboot right this second, you have to move down the defense in depth ladder. Rung 2 is an LD_preload shim, specifically the noafalge.so library. What this does is intercept the lib socket calls and kick back a permissions error, globally blocking all the published POCs. Then we have Rung 3, which is applying its systemd drop-in config, specifically restrict address families equal to AF_AUG. This slaps a strict kernel-level block on that vulnerable interface for specific daemons.
All right, here are the most critical, immediate steps you need to take right now to protect your perimeter. Number 1, deploy that AFOG defense shim RPM if you can't immediately reboot your fleet. Number 2, apply those systemd drop-ins to load-bearing units. Think SSH and your container runtimes. Next, get your audit rules set up to monitor for the creation of socket domain 38, that's AF_AUG. Legitimate hosting workloads like Nginx or PHP, they do not use AF_AUG, so a hit there is a highly fidelity indicator of compromise. You also need to run Otis direct page cache integrity scans to hunt for any memory divergence against the disk. Oh, and a quick heads up, CISA has mandated that all federal civilian systems must have these fixes applied by May 15, 2026.
And that brings us to the core philosophy of why we're dissecting this threat out in the open. The white hat code is pretty simple. Users need to know so they can protect their systems. Yes, we practice coordinated vulnerability disclosure, but once a zero-day is actively being weaponized out in the wild, playing the obscurity game only helps the adversaries. By sharing this precise intelligence openly, we strip attackers of their operational advantage, we force the vendors to issue patches way faster, and we give operators, you guys, the exact technical mechanisms needed to defend your environments today.
Look, the window between vulnerability disclosure and active weaponization, it's completely closed. The tools to detect, mitigate, and neutralize CVE 2026-31431 are literally in your hands right now. So execute the mitigation protocol, patch your kernels, and crucially, verify those reboots so the patches actually take effect. Do not let some decade-old performance optimization be the reason your entire network falls. I'll leave you with this final provocative thought. In a modern shared kernel cloud environment, are you truly trusting your workload isolation? Or are you just hoping an attacker never looks too closely at your underlying host? Execute the mitigations, stay secure.